welcome you in the lecture series of random processes, detection and estimation. It is 12th lecture of this series. In the previous lecture, we have discussed about receiver operating characteristic, base risk and base detector. In this lecture, we will discuss about the maximum likelihood detector and the map detector. The outline of this lecture are: we will discuss here the maximum likelihood ML detector, maximum a posteriori probability map detector and Minimax detector. And in the objective of this lecture, you will able to explain the maximum likelihood detector, and you will also able to explain the map detector and Minimax detector. Now, first we will start with the maximum likelihood detector. We know from the previous lecture that critical region R1 is the set of all sample points which decide H1, and the likely and conditional likelihood ratio will be greater than, less than, is equal to probability of H0 by probability of H1. These are the prior probabilities. So if the prior probabilities are equal here, and C00 is equal to C11 is equal to 0, means no cost for the correct decision, and C01 is equal to C10, it is equal to 1. So in this case, if you are having the prior probabilities are equal, then we will decide H1 or H0. If the probability, conditional probability x by H1 greater than Px by H0, then we will decide H1, and the probability x by H1 less than probability x by H0, then we will decide the hypothesis H0. So we choose the hypothesis with large conditional likelihood, or one of the maximum Px given Hi. This is known as the maximum likelihood detector. Actually, it should be maximum conditional likelihood, but we don't use this term in usual sense. Now, another detector is the maximum a posteriori probability map detector. You know, the conditional likelihood ratio to decide H1 or H0 will be greater than or less than the ratio of the prior probabilities Ph0 by Ph1. And from the base theorem or base rule, we can write it as probability H1 by X and probability H0 by X greater than, less than the prior probabilities Ph0 by Ph1, and this is the threshold value which is depend on the prior probabilities. So we decide here, if H1 and Ph0 is equal to Ph1, then we decide H1 or H0 as probability H1 by X greater than, less than the conditional probability Ph0 by X. So here these are the prior probabilities Ph0 and Px1, and Ph1 by X or Ph0 by X are the posteriori probabilities, means probability that is computed after the observation has been made. And so this detector, which minimizes probability of error for any prior probability, is termed as map detector. And for the map detector, Ph0 by Ph1 is the threshold value, as you can see here, is the threshold value for map detector. And if Ph0 is equal to Ph1, then the map detector reduced to the maximum likelihood detector. Now consider example. Consider the binary communication problem where we transmit S0 0 is equal to 0 or S1 0 is equal to 1, and there are two hypotheses at the receiver. The hypothesis H0 corresponds to X0 is equal to omega naught, and H1 hypothesis corresponds to X0 is equal to 1 plus omega naught, means DC level in the noise, and where omega naught is the white Gaussian noise with zero mean and variance 1. And at the receiver, we observed that Px0 is equal to 0.6. So this is a similar question in the previous lecture. And using ML test, determine which signal was transmitted. In the previous question, we have used the NP test, and here we will use the maximum likelihood test to determine which signal was transmitted, and also find out the type first and type second error. Using ML test, we decide H1 or H0 if the conditional likelihood ratio greater than less than 1, the threshold value, or you can write it as Px H1 divided by Px H0, the joint probability under hypothesis H1 and joint probability under hypothesis H0 greater than less than the threshold value 1. So here, because the two hypotheses are equally likely, is Ph0 is equal to Ph1. So here the threshold value is 1, and so you can write after solving this likelihood ratio is to the power x0 minus 1 by 2 greater than less than 1. So it can be x0 greater than less than 1 by 2 plus log e1, and value of log e1 is 0. So x0 greater than 1 by 2. This means when x0 greater than 1 by 2, then we will decide h1, and when x0, the observed sample, less than 1 by 2, then we will decide h0. And the given, you have given that x0 is 0.6, and you know the 0.6 is greater than 1 by 2. So this test decide the signal 1 was transmitted. But in the previous lecture, when we have used the NP detector, for the NP test, we have shown that the detector decide 0 was transmitted. But in this case, using ML test for the same question, it decide that 1 was transmitted. So now we will discuss about the type first error. Type first error means probability of false alarm, means probability of deciding the hypothesis H1 when H0 is true. So it will be the probability of X0 greater than 1 by 2, because we have decided H1 and given H0 is true. So it will be integration 1 by 2 to infinity, and the PDF under hypothesis H0 1 by under root 2 pi is to the power minus x square by 2 dx, and it will be 1 minus 5 1 by 2. So from the table you can find out the value of this is 0.308. So the type first error is 0.308. And for the type second error, you know the type second means the probability of H0 when H1 is true, means the probability of observed sample less than 1 by 2 when H1 is true. This means the integration minus infinity to 1 by 2, and the PDF under hypothesis H1, it is 1 by under root 2 pi e to the power minus x minus 1 whole square by 2 dx, and it will be integration minus infinity to minus 1 by 2 1 by under root 2 pi e to the power minus x square by 2 dx. So from here you can find out it will be the cumulative function phi minus 1 by 2, and the value of this from the table you can observe it is 0.3085. So this is the type second error. Now consider the same question. We transmit either S0 or 1, and the two hypotheses H0 correspond to there is no signal, only noise present, and under the hypothesis H1 the signal is present with the noise, and mu and omega naught is the white Gaussian noise with 0 means and variance sigma square. At the receiver we observe x0 is equal to 0.6. The question is same as the previous question, but here you have to use map test to decide which signal was transmitted, 0 transmitted or 1 was transmitted. If Ph0 2 by 3 and Ph1 1 by 3, means the probability of hypothesis H0 is 2 by 3 and probability of hypothesis H1 is 1 by 3, means the probability of getting only noise is the 2 by 3, and probability of getting signal in the noise is 1 by 3. And also find out the type first and type second error. So from the map test, we decide H1 or H naught if the conditional likelihood ratio means probability P H1 given X by probability P H naught by X greater than less than P H naught by PH1, the prior probabilities, and the prior probabilities are given 2 by 3 and 1 by 3. So the threshold value is 2. So from here you can find out e to the power x naught minus 1 by 2 greater than less than this threshold value 2, and after taking a natural log you will get x naught greater than less than 1 by 2 plus log e2. This is the new threshold value, and it will be 1.193. This is the another threshold value. This means when x naught observed sample greater than 1.193, then we will decide H1, and when x observed sample less than 1.193, we will decide H naught. And you have given x naught is 0.6 and it is less than 1.193. So map test decide the signal 0 was transmitted. So in the previous two questions we have seen that for the same question, when we apply NP test, then it decide that 0 was transmitted, and for the ML test for the same question we will decide that 1 was transmitted. And for the map test we can see that using the map test the signal 0 was transmitted. So for the NP test and the map test 0 was transmitted, and for the maximum likelihood test 1 was transmitted. And now type second error. Type second error means the probability of selecting H1 when H naught is true is probability of observed sample greater than 1.193 when H naught hypothesis H naught is true. This means integration 1.193 to infinity, and the PDF under hypothesis H naught means 1 by under root 2 pi e to the power minus x square by 2 dx. So it will be 1 minus phi 1.193, and from the table the value is 0.1164. And so the type first error is 0.1164, and the type second error means probability of selecting H naught when H1 is given. So you can say that the probability of observed sample less than 1.193 given H naught H1 is true. So this means minus infinity to 1.193, and the PDF under hypothesis H1, this means 1 by under root 2 pi e to the power minus x minus 1 whole square by 2 dx. So I can write this integration as minus infinity to 1 minus 1, this is 1.193 minus 1, so it is 0.193. So from minus integration from minus infinity to 0.193, and 1 by under root 2 pi e to the power minus x square by 2 dx, and this is phi 0.193, and from the table of cumulative distribution function you can find out the value is 0.5765, and we have shown how to measure the value from the cumulative distribution function table. We have already shown in the previous lectures, and this value is second type error is 0.5765. Now the Minimax detector. The base rule assign cost to the decision and have the knowledge of the prior probabilities. In a situation when we have no enough information about the prior probabilities, the Bayesian decision rule cannot be used. In this case, we can assign a value P1 to the prior probability of hypothesis H1. So means we have to assign the value P1 to the hypothesis H1 for which the risk is maximum. Then minimize the risk function. The rule of minimizing the maximum average cost for the selected P1 is referred to as the Minimax rule, and the detector based on this is known as the Minimax detector. You know, the bias risk is C00 P, the conditional probability P H naught given H1 probability H naught plus C01 probability H naught when H1 is given P H1 plus C10 conditional probability H1 when H naught given and probability H naught plus C11 P H1 given P H1 and probability of H1. So we know the conditional probability Ph1 when H0 is given, it is the integration in the critical region, because we have decided H1 and H0 is 2 is the PDF under hypothesis H0. So Px by H0 dx, and it is known as the false alarm probability. And Ph0 conditional probability Ph0 by H1, it is the integration with the region R0 and Px by H1 PDF under hypothesis H1, and you know this is known as the miss probability, or you can write it as the 1 minus the probability of detection. And probability H1 by H1 means you have taken the correct decision H1 2 and you have decided H1 means the integration in the critical region R1, and the PDF under hypothesis H1 is the probability of detection, and the Ph0 by H0 is the integration in the region R0, and PDF under hypothesis H0 it will be 1 minus PF, 1 minus probability 1 minus probability of false alarm. So now let P0 and P1 are the prior probabilities of the hypothesis H0 and H1 respectively. Then the base risk can be given as C00 1 minus probability of false alarm into P0 plus C01 1 minus probability of detection P1 plus C10 PF P0 plus C11 probability of detection plus P1. P1 is assigned to the hypothesis H1. Since P0 plus P1 is 1, P0 plus P1 is 1 here, and P0 is equal to 1 minus P, so I can write R is equal to C00 1 minus PF plus C01 PF P0 and plus C01 1 minus PD plus C11 PD P1, or I can write the base risk is equal to C001 minus PF plus C10 PF plus P1 C11 minus C00 plus C01 minus C11 PM minus C10 minus C00 PF, and the base test decide H1 or H0 if the conditional likelihood ratio greater than less than, you know, this is C10 minus C00 upon C01 minus C11 1 minus P1, and P1 means this is the prior probability of H1 and this is prior probability of H0. This is we have assigned this is P1, and so it will be 1 minus P1. Also here P1 not equal to 0 and P1 not equal to 1 in this case. This means P1 belongs to between 0 to 1. When P1 is equal to 0, the threshold will be infinity, and we always decide H0, and in this case PM is equal to 1, PF is equal to 0, and the base risk R will be equal to C00. And when P1 is equal to 1, the threshold value will be 0, and we always decide here H1. We will take the decision in favor of the hypothesis H1, and in this case probability of miss is 0, probability of false alarm is 1, and the base risk is equal to C11. And if P is having some value P1 star and here P1 star belongs to between 0 to 1, then you can see the test for P1 equal to P star gives the minimum risk R minimum. Here is the minimum risk, and the target to R minimum is the horizontal, and P star R star P1 at P is equal to P star represent the minimum cost. So for the Minimax rule, the C11 minus C00 plus C01 minus C11 PM minus C10 minus C10 minus C00 PF will be equal to 0, and if the cost of correct decision is 0, means C00 minus C00 minus C11 is equal to 0, then the Minimax rule for P equal to P1 star, it will reduce to C01 PM is equal to C10 PF, and here if C01 is equal to C101, if the cost of the incorrect decision is 1 here, the Minimax rule at this point P1 star, it will reduce to probability of miss will be equal to the probability of false alarm, and the Minimax cost will be the bias risk is equal to PF1 minus P1 plus PM P1, and you can write it as PF P0 plus PM P1, and which is same as the average probability of error. Now let us consider example. Let y a random variable that has PDF under each hypothesis H. In the hypothesis H0, P0 y will be will having the PDF e to the power minus y uy. This is uy is the unit step function here, and under hypothesis H1, P1y will be under root 2 by pi e to the power minus y square by 2 and unit step function. And let C00 is equal to C11 is equal to 0 and C01 is equal to C10 is equal to 1. So the cost of error is 1, and there is no cost for the correct decision in this case. So find the Minimax decision rule to decide H1. So you can see here this is the graph for P0, yellow graph for P0y, and this green graph for P1y, and let there is threshold gamma, and if the threshold gamma we have decided, the probability of miss will be, because the probability of miss means we have decided H0 when H1 is 2. This means this region from 0 to gamma, integration from 0 to gamma under root 2 by pi e to the power minus y square by 2 dy, and the PDF under hypothesis H1, and it will be and the probability of false alarm will be integration from gamma to infinity e to the power minus y dy, means integration means PDF under hypothesis H0. And for the uniform cost, you know, PF is equal to PM. So putting these two integration equal, then we will get 1 under root 2 by pi 1 minus q gamma is equal to e to the power minus gamma, and after solving this you will get the gamma is 0.565. the threshold value is 0.565. So the Minimax decision rule decide H1 if gamma greater than 0.565, and the Minimax rule decide H0 if this value y less than 0.565. So this is the Minimax rule. So far in this lecture we have discussed about maximum likelihood detector, maximum a posteriori probability detector, and Minimax detector. This was the 12th lecture of the series of random processes detection and estimation. In the next lecture we will discuss about multiple hypothesis testing and composite hypothesis testing. Till then, thanks for listening this lecture. Thank you.